Hi, I'm Andrew Parnell, and I'm a physicist at the Department of Physics and Astronomy at the University of Sheffield. And today we're going to talk about the very big and the very small. And my research is focused on the very small, on the nanoscale. And I do experiments looking at materials and matter on the nanoscale and biological materials as well. And that's my thing. I study materials and look at their structure and their function to try and understand how we can make materials that are better, solar cells that are more efficient, or understand how we can learn from butterflies and birds, how we can turn the structures that they have that make these amazing colors that are very permanent, and how we can use those to make synthetic materials that have long-lasting and similar properties, and hopefully lessen the carbon footprint when we try and make materials in the modern world.
Hi, I'm Paul Evans. I'm an artist based at Yorkshire Art Space in Sheffield. And my role here is to help create some visualizations, really, to take the beautiful ideas that exist in science out of people's minds and bring them out into the real world so that we can see them. When we see them, we can talk about them. And I've been working with Andrew and Professor Richard Jones on a number of projects since about 2015, creating art and creative public engagement projects, working with schools based around their research. I've worked with many institutions around the UK, a number of universities, and also institutions like the Wellcome Trust and the BBC. And I'm fortunate enough to work alongside scientists on projects that create a positive effect in the world. So new types of solar cell, like Andrew was just talking about, paints that lessen environmental harm, and recently creating a virtual ark for endangered species.
So in this film today, we're going to be exploring the very big and the very small, sort of a fantastic journey that takes in the things that we have in our solar system. So the largest object, which is the sun, and how that object is responsible for the life on this planet. And so that will incorporate actually going down to the nanoscale, so going down to the quantum scale, some of the smallest things that exist in the natural world, and looking at the particles that we use to transfer that solar energy, that sunlight, that's so important into food and into energy, into electricity. And so I think it's quite interesting to think that the largest object actually, that powers our energy needs of the planet is actually, we actually have to go down to the very smallest scales, down to the atomic level, down to the quantum scale, to give us our energy. And actually the process by which the sun creates that energy or produces that energy involves the process of fusion. And we'll see that in one of the films that we'll show in a few moments. But also on a biological level, we think of how plants rely on photosynthesis, so taking light from the sunshine and turning that into energy, into carbohydrates and other foodstuffs that we eat, and again are so important to our world and our lives, and often taken for granted.
Right, so what we're going to take is a kind of journey through physics, about how we might understand physics, kind of on a personal level. It's a little bit about how I've come to peace with a subject that I struggle to engage with at school. And I've been helped on this journey towards a sympathetic understanding of physics, towards a common understanding, if you like, of what it is, about what's possible to understand about physics, beyond the equations, beyond the maths, and what's important to understand about physics. And quite often we've been having discussions about understanding, Andrew and me, and I think it's quite worthwhile to think about the origin of that word understanding, which kind of means to stand in the midst of, from the Old English. And it's been great to do that quite literally, while scientists have been involved in their journeys of discovery, making their observations, discussing their research with them on a very very personal level. Following these journeys of discovery, like a ship's artist on those great journeys of discovery in the past, like Darwin on the Beagle, or Alexander Humboldt on those great journeys of discovery. I've been like a kind of ship's artist on those journeys, and it's a journey between objects, what we perceive as solid objects. What is solidity? We kind of like to think that this table's solid, but I mean, in a way, when you learn about physics, you learn that that's kind of on a very small scale. That's a questionable notion. Also, the space between objects, the 150 million kilometer distance from the Earth to the Sun, and then kind of inner space. The infinitesimally small distance between particles.
So I'm going to pick up there, Paul. I think as a physicist, we like to think of not just as particles, but if we think of solid objects, we like to think of atoms. So things that are like our materials that we encounter, they tend to be, atoms that normally have fixed positions and things. So that's sort of a technical difference in terms of language between a particle and an atom, is the fact that these things have got solidity and they're not just whizzing around. We think of particles. We tend to think of particles as whizzing around in space, or whizzing around, like Brownian motion, under a microscope.
Yeah, I understand what you're saying, but I really do like that word, particles. I think I read recently that it comes from the Latin, so it means a very small part or piece, a kind of grain of matter, like a grain of sand. So those grains might make up a really big thing. If you think about a beach, when you look at a beach from a distance, maybe from a cliff top or something, you see a beach. You have to get really close, to see those grains of sand that comprise that thing that we call a beach. And I think to a certain extent, it takes a bit of imagination to make that leap. Do you know what I mean? And that's what I hope, I bring.
And I think what we're going to see today, in some of the footage that we're going to see, I think what Paul's done is really helped to visualize things that I find really hard to, even as a physicist, find it hard to differentiate between the big objects in our solar system, such as the planets, Jupiter, and the Sun, and the very small. So like I think in our human existence, we're able to look at things such as an apple or a table. And we are very visual creatures in the sense that we take in information through our eyes and through our touch and sensation. So in terms of being able to go, all these many different orders of magnitude and length scale from the huge distance that Paul just said about how far it is to the Sun, for us that's quite an incalculable or a hard to imagine distance, and the same is true of how small things are on the length scale of the atomic level. So
there's something about humans being in the middle of this scale, isn't there, Andrew?
I think there are some sort of good reasons why biology works on this level. We're about the right size. And I think, in terms of our perception, though, which I think is probably crosses over quite nicely with the artistic world, is that, we do perceive and learn by looking at around us, and the scale on which we are is the scale of life. And I think that's a quite an intriguing aspect that it affects not just, physicists still have to come to grasps with some of these big problems in terms of, how big objects are, and the nanoscale physics that is down there at the very small level.
So what is physics, Andrew?
I'm an experimental physicist, so to me, I perform experiments and trying to understand the physical world around me, and the material world around me by looking at the materials and the way in which they work. So for me, I perform a lot of experiments and try and understand. Often my experiments are very simple because that's the way we like them. We can have more insight and more predictive power if we have very well controlled experiments. So looking at how you make a solar cell, you make it from many different materials, and then by looking at the effect of heating that solar cell or processing it with different temperatures and stuff, you can start to understand what it is you've done to it. And we tend to look at the nanostructure of those materials using X-rays, neutrons, or very powerful atomic force microscopes. So to try and link the nanostructure or the morphology of that structure to the overall performance and properties. And I think that's key for us. There's a book called Form and Function that talks about biology, and I think as a physicist, I'm very keen to look at structure and function. So those two, to me, I think that's the overlap between biology and physics, in the sense that there's a strong link between how you put materials together, or how materials are formed, or their structure that they have, and their actual performance.
Okay, so let's get back to this idea of journeys, and one of the journeys that Andrew and I have kind of taken together. And when we think about journeys, we might think about a starting point as a destination, a kind of linear journey, straight line journey. We can also travel on a more meandering path, and I think to a certain extent some of the thoughts that we're going to consider during this film will follow a slightly meandering path. But let's begin with a linear journey between the sun and the earth. So let's show the first film, which is Harvesting Light.
So in this film, we're going to see the process of light being made or produced in the sun, the heart of the sun in the fusion reaction, and then it interacting with us on Earth, and showing us how we can take that that free energy that we get from the sun and turn it into electrical energy, which is obviously so important in this time of switching to energy that doesn't burn fossil fuels. So using the free energy that we're bathed in throughout the year, 24/7, 12 hours a day essentially, but we still get all this amazing energy. So here we are at the heart of the sun. We're moving inwards. We'll start to see the hydrogen atoms, which are jiggling around and being forced together and overcoming the strong repulsive forces that you have in the atomic world, at the atomic length scale. And you're starting to fusing them together to make little deuterium atoms of heavy hydrogen. And then this process, it takes place, and we're trying to replicate this on Earth to try and make free and long-lasting energy. But it's still very hard, but it can be done. And so now we've fused them together, and that fusion reaction has created this amazing bath of energy, and as a consequence, we get light as well. Now we see that light traversing the void between the distance between the sun and the Earth. Incalculable distance. Well, not incalculable, but it seems like an immense distance to the human mind. But it does come all the way to us. So we see this oscillating waves. This is what we understand how waves propagate, and what we learned from Maxwell's equations a long time ago. And here we start to see it entering the upper atmosphere. So some light is obviously not transmitted through, but this is the solar sunlight that gets bathed, and now it's traversing into the quantum world, into the very small world, where the physics that's really important to turn this energy from these excited states into that are created by the absorption of the sunlight into electrical energy. And here we have them sort of traversing around, trying to find an interface where they can recombine and then be returned. So here's a recombination, and we can see that energy that was originally light, a photon, being turned into electrical energy in this meshwork here, that nanoscale meshwork. And here we see the contacts of our solar cell. So that electrons are being, we've got like a electrical cell, and that's what's giving us our energy, the ability to charge devices and do useful things without the burning of a stinky, horrible fossil fuel. And yeah, just to say those great people are involved in it, Human and Richard Jones and Michael Weir, who are not here today, but yeah, excellent.
Yeah, so just to reinforce that, the film began as a series of conversations between Andrew, Professor Richard Jones, and myself. I then made some drawings, visualised what was described as some very difficult physics, and then we fed those drawings into Human VR in Sheffield, where they created that fantastic visualisation in their Sheffield-based studio. Right, so let's try and imagine the scale of that journey here's an analogy. The average walking speed of a human is about 5 kilometers per hour. The sun is 130 million kilometers away. So that's about 30 million hours, which is around 3,400 years, assuming you walk 24 hours a day, 365 days a year. Anyway, that's a kind of analogy. I'm not sure if it's a good analogy. What do you think, Andrew?
I don't think it's helpful. I think it's like I said earlier, as a human length scale, it doesn't quite fit. What I prefer is the idea that it takes 8 minutes 19 seconds to get for that light that's created in the fusion process to get from the sun to the Earth. I think that's a really, we know how fast light travels, so it's instantaneous. So that I think that 8 minutes 19 seconds is a to my mind, it's just like it's a fantastic distance, but it gives us sort of a surety that we know that the sun's always shining, and that is a constant supply of energy that we can use. The other thing is so that's the very large scale, this huge distance that Paul said would take you nearly 3,500 years to walk if you walk 24 hours a day. The other thing is that we like to think about, and what we showed in that video was the very small. So this idea that that to abstract that light and turn it into energy, that sunlight, we need to go down to the very small nanoscale. So the other idea is to get across how small that nanoscale world is. So we thought, pick up a A4 piece of paper and then divide that up by 1,000 times, or 10,000 times actually, and you're starting to get down to the level at which you're really things that you get approaching the nanoscale world. But that I think is quite, again, it's like we say, we live at this human length scale. So these two extremes are actually quite hard to comprehend. But I think this is what this talk is about. It's about trying to understand how important these length scales are to our everyday world. So.
Okay, so the next film we're going to show was commissioned for the Festival of Mind 2018. The Festival of Mind is this fantastic event that occurs every 2 years in Sheffield, run by the University of Sheffield, where artists are invited in to interpret or otherwise engage with university research and create often really brilliant and exciting works of art. And I've been very, very fortunate to have been involved in this festival right from the beginning. So this next film was commissioned for the Festival of Mind, and now we'd like to play the Delft Service, which is another short film. Do you want to explain what's happening here?
So these are patterns. So this is when we said earlier that these structures are so small that we can't use normal light to image what's going on inside some of these materials, these nanoscale materials. So we use scattering, the process of scattering X-rays and neutrons, and that will inform us about the kind of structures that we see, which I think is really quite amazing. We see, this is how the shape and the double helix structure for DNA was discovered, and I think it's quite fantastic that we can actually start to, just by shining X-rays and neutrons onto materials, we can start to see the inner nanostructure, the inner atomic structure, these amazing patterns. And I think that's really quite, really very powerful probe of understanding this sort of mysterious world of the nanoscale that is so important to the material properties that we use every day in our existence.
Okay, so for me, I just want to talk about that film, which is again created with Human Studio in Sheffield. All of the films that you've seen today have involved they're working with them, collaborating with them. So this film you've just seen is called The Delft Service. The reason for that is because initially I took the name from The Owl Service, which was a book by Alan Garner. It's a very haunting book about plates that are kind of haunted with a pattern, and tracing the pattern from the plates brought something to life, a kind of ancient entity. And I thought there's something that I was seeing in in this way of creating images that felt like that. So it's two ideas brought together, I suppose. The idea of this book, that was in my mind, The Owl Service from my youth, and then the idea of creating something as a plate, as a service of plates, and then the blue that's there. That's the Delft blue that was used in Delft, in Holland. A particular colour that a rather beautiful colour that if you like, identified that particular way of decorating ceramics. There's something about, I think there's something that Einstein said about spooky actions at a distance, from about quantum mechanics. So bringing those two ideas together, and there happens to be a reactor institute in Delft, where this imaging takes place. I was fortunate enough to visit a similar facility in the south of France, with some of Andrew's researchers, and this is where another experiment took place, which I was fortunate to actually observe taking place in real life in the south of France. So what I'd like to do is play another film that resulted from that experience. So if you can play Neutron Spin.
This is a very abstract but somewhat beautiful interpretation of how these particles, these probes of matter, these neutrons are interacting with this material, this sort of monolithic porous structure, which is actually taken from a fantastically ultra-white beetle. And the idea was to try and understand what makes this beetle so white. So by probing the structure, we were able to understand how to take this natural biological material and how we could make it synthetically. So those Paul's and Human's amazing interpretation of that process is actually what gives it such great power. I think the sort of abstract beauty of these spinning tops of neutrons, which is actually very similar to Paul alluded to quantum mechanics. That's the quantum mechanical behavior of these neutrons they're processing, and by interacting with that material, that alters their precession, which is very these are particles whizzing through a quantum mechanical behavior, and they're actually interacting with that material and giving us a probe of matter that's very, very powerful. And like I should say, that technique was actually pioneered at the Reactor Institute Delft, and they've really come leaps and bounds into helping to understand materials and materials physics. So I think that's really a very powerful way in which we could understand how to understand materials and also develop new materials by probing their structures using these sort of amazing techniques. And Paul certainly did have a great time working at the SRF and seeing I think he described it sort of utopian way in which the physicists and the material scientists and engineers went about understanding materials by probing them with these X-rays probes and neutron probes.
So with a conversation with Professor Richard Jones some time ago about a new material that had been discovered called Vantablack, which is the blackest black. You've probably heard this story about the artist Anish Kapoor basically claiming exclusive rights, or securing exclusive rights of the use of this material. It's quite an extraordinary stuff because basically it absorbs nearly all wavelengths of light. So when you look at an object that's kind of coated with Vantablack, there's no surface reflection or anything like that. So it's like a hole in space. It's like a black hole. Quite extraordinary stuff. But then I found out that, well, basically I've gone along with this, this interest in this blackest black, but then found out that basically we couldn't use it. But Richard said, well, we are working on a very white. So I thought, well, perfectly happy with the whitest white, a second. coming second to the black is black. In a way, that was how that began. So that's yeah. We ended up looking at this sample from this extraordinarily white beetle, and this idea of superlative colours, I thought was really quite neat. I don't know if you're aware, but that story about Anish Kapoor having exclusive right over Vanta Black, that's kind of run and run. And there's an artist now called Stuart Semple who's produced a range of superlative colours. Pink is pink, and on that pink is pink, there's a note which says, by adding this product to your cart, you confirm that you're not Anish Kapoor. You're in no way affiliated to Anish Kapoor. You are not purchasing this item on behalf of Anish Kapoor or an associate of Anish Kapoor. To the best of your knowledge, information and belief, this paint will not make its way into the hands of Anish Kapoor. So anyway, we have a range of superlative colours that are kind of fought over now in the art world. But this topic of superlative colours led to the development of the first work of art that I worked on with Andrew and Richard. So we'd like to play the last film, which is Homage to the Sphere. Okay, it's quite hard to describe this one, really. But what we've got here is a three-dimensional representation of a colour wheel. You've probably seen a colour wheel where you have all the hues going around the outside. You might have noticed that things get grayer towards the middle, right? Now, if you take that two-dimensional colour wheel and turn it into a three-dimensional solid, you get essentially a three-dimensional colour sphere, right? So what we've created there is a three-dimensional colour sphere, and each colour, if you like, has got its own kind of room. So it starts with the brighter colours at the outside edge. They get kind of grayer towards the middle, and there's a kind of axis down the middle that goes from white at the top to black at the bottom. So yeah. Now the reason it's called Homage to the Sphere is because there's a series of paintings by a painter called Joseph Albers called Homage to the Square, and they were all basically experiments in juxtapositions or how you put colours together, colour harmony experiment. Okay, I think they're kind of coming to the close now, but I wanted to sort of finish with a poem. We've actually worked with poets on projects in the past. In particular, a book called The Rose of Temperaments that was created with the help of Longbarrow Press in Sheffield and a number of poets. So yeah, look up Longbarrow Press. You'll find it on there. And so the poem goes: Do not all charms fly at the mere touch of cold philosophy? There was an awful rainbow once in heaven. We knew her woof, her texture. She is given in the dull catalogue of common things. Philosophy will clip an angel's wings, conquer all mysteries by rule and line, empty the haunted air and nomad mine, unweave a rainbow as it erstwhile made the tender pursed Lamia melt into shade. Right. That's a narrative poem written by, it's a short piece from a narrative poem written by the English poet John Keats, published in 1820. It's kind of got a mythological kind of context. But I think there's an interesting idea in there, which is this idea of science, if you like, taking the beauty and mystery out of the world. And I disagree with that so very strongly. There's an idea in a way that there's two cultures, art and science, you know, and in a way, you could say that I operate, if it was a Venn diagram, like a figure of 8 like that, and it was a Venn diagram, I'd be operating in that kind of area between the two cultures, art and science. But you see, I don't really think this works. I think it's what we call a category error in philosophy. If you were to draw a big circle around that figure of 8, that's the culture that we occupy. And I can't really understand why science engenders such fear and suspicion. I don't think there's anything frightening about learning more about things. I think all it does is enrich the woof and weft of the world. In the poem, Keats is referring, he's using this kind of weaving analogy of woof and weft. And I think the world is a complex textile that's woven out of so many interesting things. And the more that we learn, the more we're kind of in the world, the more we're kind of part of it, and the more we know about the world, and the more beautiful it is. How would you counter that argument?
I think, I think, Paul, but I think in terms of beauty and aesthetic, I think we can only, those are all quite, artistic concepts, beauties and aesthetic. But as scientists, I think we don't rob the mystery or the majesty of the natural world by understanding it some more. And I think that's our great endeavor, I think, in terms of scientists, to try and understand more, because it does help to better civilization. And I think that's essentially what scientists should be doing. We've only seen recently how great science is at trying to conquer a terrible virus. And I think that the sort of international effort that was put together to be able to do that is truly a testament to the international nature, which is science. And I think that is something that, in a world where we are getting more insular sometimes, I think remembering how great science is at understanding patterns, nature, form and function, and probing the very big, the very small, in a sort of collaborative way is only ever to be applauded. And I think I enjoy being a scientist, and I'm very fortunate as a human to be able to do the science that I do and get to work with all these people. And I think Paul and I have been very fortunate as well to impress upon this in a very not in a very heavy-handed way, but we've taken some of these concepts to school children across the north and east and Lincolnshire as well, and they've really embraced it. And I think this kind of idea that understanding nature and the natural world, the physical world around us is something that people engage with. And I think some of the concepts that we've tried to get across to you today about understanding the natural world, on a very small scale and on a very, very big scale, are very, very difficult to do. But I think in terms of the visuals that Paul and Human and all the great people we've worked with, Richard Jones and Mike Ware, have all helped us to try and convey these very interesting abstract structures and morphologies to people. And that, I think, has been our great journey from the very big to the very small and back again. And I think that's why it's been such a pleasure and an ongoing testament to our working relationship, that we can keep reinventing and revisiting things and looking at things with new eyes and things. So yeah, that's my take on it, Paul. But yeah, I do think that nature has got more to offer, and beauty is there, and it doesn't get denuded by understanding it.